So in this video I'm going to talk about the questions which appeared, question from thermal and statistical mechanics, which appeared in which occurred in GATE 2017 examination. So let's continue with the first problem. The statement is, consider a triatomic molecule of the shape shown in figure in 3 dimension. Okay, so we are having a triatomic gas molecule which is non-linear. So that's the first point that we must note here. We are having a non-linear triatomic gas molecule. Okay, the heat capacity of this molecule at high temperature, and it's given that temperature much higher than the vibration and rotation energy scale. So it's important to note this point. Okay, so let's try to figure out what is the heat capacity of this molecule at high temperature. Okay, so if we just take a look at the translation degrees of freedom. Okay, the translation degrees of freedom, translational degree of freedom of this molecule, that is equal to Ft, that is equal to 3. Okay, because the molecule, it can move freely like a one single unit. Okay, so that's why 3 translation degrees of freedom. And then come to the rotational degrees of freedom, TATIONAL, rotational degree of freedom. So let's denote them as F rotational. Okay, because it is a 3-dimensional molecule, so therefore instead of 2 we will have 3 rotational degrees of freedom here. Now the vibrational degrees of freedom, vibrational degrees of freedom, I will denote that as FV. So first of all, let's try to understand the diatomic molecule here. Okay, suppose this diatomic molecule, it's vibrating. Okay, vibrating at high temperature, so that it will have 2 different kinds of energy terms. One is the kinetic energy term, plus the second one is the potential energy term. Okay, the kinetic energy term, that comes into the picture because of the the motion of these 2 atoms which are connected together through a certain force constant, you can say. Okay, and then the potential energy come into picture because of the interaction between these 2 atoms basically. Okay, so therefore we conclude that each bilateral pair, it contributes to different energy term. One is the kinetic energy and another one is the potential energy term. So we will call this as a one mode of vibration. Okay, so one mode of vibration consists of kinetic energy as well as potential energy. So here, when we consider this diatomic nonlinear gas molecule, so we are having one vibration pair, the second vibration pair, and then the third vibration pair. Okay, so in total we are having 3 vibration pair, where each vibration pair will contribute kinetic energy and potential energy. So in total there will be 3 modes of vibration, 3 modes of vibration, with each mode of vibration having 2 energy term. Okay, so in total we will have 6 energy term. Okay, 6 square energy term, you can say 6 square energy terms. So here we will call this, each square energy term we will call as the degrees of freedom. So I will write it here 6. Please note that these 6 energy terms, they are equivalent to 3 modes of vibration, 3 modes of vibration. Okay, so that's the point that you must understand here. Okay, because each vibration mode, it consists of kinetic energy as well as potential energy. Okay, so in total, the total degrees of freedom, total F, that is equal to 3 plus 3 6 plus 6 12. Okay, so from equipartition theorem, we know that each degree of freedom contribute, a single degree of freedom contribute half kT to the total average energy of the system. Okay, so here the total energy of the system, that is U, that is equal to the number of degrees of freedom, which is 12 multiplied by the contribution from each one single degree of freedom, that's 1/2 kT. This is 6 kVT. Okay, so that means the heat capacity contribution, that is equal to du by dt at constant volume, so that is equal to 6 kV. So therefore option D is the correct one here. So let's take a look at the next problem. A reversible Carnot engine is operated between temperature T1 and T2 such that T2 is greater than T1. So we are given a situation where T2 is greater than T1. So let's say this is T2. This is a reservoir at a higher temperature, and then we are having the second reservoir which is at temperature T1, but now the T1 is lower than T2. So here let's assume that Q2 is the amount of heat that's taken by the working substance while going through the cycle. Okay, so Q2, and let Q1 is the amount of heat which is directed to the low temperature reservoir, and W is the accordingly the work done that is achieved during this process. So W here, that is equal to Q2 minus Q1. Okay, now with a photon gas as a working substance, so here it's given that it's a photon gas that's a working substance. The efficiency of the engine is, we know that the efficiency of the heat, such a heat engine, that is equal to 1 minus the temperature of the reservoir which is at the lower temperature. Okay, so that means here the lower temperature is T1, 1 minus T1 upon high reservoir, the temperature of the reservoir which is larger, so 1 minus T1 by T2. Okay, so note that the efficiency of the Carnot heat engine, it is independent of the nature of the working substance. It doesn't matter whether we are taking a photon gas or real gas or some other gas, the efficiency, it's not going to be affected by the nature of the gas. So therefore V is the correct option here. So let's continue with the next problem. The statement is water freezes at 0 degrees Celsius at atmospheric pressure. So we are given the data, what the pressure at which water freezes, P1, that is equal to 1.01 into 10 power 5 Pascal. The density of water and ice at this temperature and pressure are respectively, they are given to us. So rho 1, let's call okay, so because the pressure which is required for depressing the melting temperature of ice, so that means here we are concerned about melting of ice into water. Okay, and it's given that the density of ice, that let's call that as rho 1, that is equal to 1000 kilogram per meter cube, and rho 2, that is equal to, that's a density of water, that is 934 kilogram per meter cube. Okay, that's the data that's given to us. Okay, and also the latent heat of fusion, LF, that is equal to 3.34 into 10 power 5 joule per kilogram. Okay, now let's try to understand. We have to find the pressure which is required for depressing the melting point of ice. Okay, so that means we have to find the new value of the pressure so that the melting point of the ice is depressed by 10 degrees Celsius. Although it's a very large change in the temperature, and the corresponding pressure that we expect, it's also going to be very large. So that's why, because the at atmospheric pressure, it's a pressure of the order of 10 power 5 Pascal, and the answer that's going to be in the range of gigapascal. So there is a nearly a 4 order of difference in the pressure, the final pressure. Okay, so we can solve this problem by making use of the Clausius-Clapeyron equation. So according to Clausius-Clapeyron equation, dP by dt, that is equal to L by T into V2 minus V1. Remember that here V1 and V2, these are the specific volume. Okay, so the specific volume, for instance, for the case of ice, so we know that density that is equal to mass upon volume. Okay, so whereas when we define the specific volume, that's V, that is equal to the volume divided by mass, then it becomes a specific volume. Okay, so in the Clausius-Clapeyron equation, B1 and B2, they refer to the specific volume. So this is inversely connected with the density, so I can write this to be specific volume, that is equal to 1 by rho, or more precisely B1 is equal to 1 upon rho 1. And similarly I can write for the water also. So V2, that is equal to 1 divided by rho 2. So now we can easily solve this problem, because the latent heat of fusion, that's also given to us, and the temperature, that's at 0 degree Celsius. T here, that is equal to 0 degree Celsius, and that is equal to 0, this is at yes, 0 degree Celsius. That means it is going to be 273 Kelvin. Okay, so that means, and what is the dt? The change in temperature that that we need to consider is, that is of 10 Kelvin. You can say 10 units of difference, 10 degrees Celsius, and that is equal to 10 Kelvin basically. So remember that it is a difference in the temperature, not the temperature in Celsius or Kelvin in a sense, you can say. So because dt, that is equal to T2 minus T1. Okay, so it's a difference between two temperatures. So it doesn't matter whether we are working with Celsius or Kelvin. When we will take the difference, so it's also all the time it will be a 10 units of difference. Okay, so from this relationship we can find the first of all we will determine what is the corresponding change in pressure. Okay, and then from there we will calculate the final pressure. Okay, so now dP, from this relationship dP, that is equal to L dt upon T into 1 upon rho 1 minus 1 upon rho 2. Okay, and that is equal to L, that is 3.34 into 10 power 5. Okay, and then temperature, that is 273 Kelvin, and then B2 minus B1. So B2 is how much? B2 is that is 1 upon rho 2. So 1 upon 934 minus 1 upon rho 1, that's 1 upon 1000. Okay, so we have to solve this. Okay, so that means after solving, so we can easily see that dP, that is equal to 3.34 into 10 power 5, and then after solving the denominator, we will obtain a factor of 10 power 5, and then okay, sorry, I didn't multiply here with the dt, that's 10 units of. Okay, so it becomes 10 power 6 in principle, and from the denominator also we will obtain 934 into 10 power 3. Okay, and then divide this divided by 273 into 1000 minus 934. Okay, and this comes out to be equal to 3.34 into 934 into 10 power 9, and then divided by 273 multiplied by 1000 minus 934. So that is equal to 66, yes, into 66. Okay, so this upon solving, that will give us an answer that's close to 0.173 into 10 power 9 Pascal. Okay, so that's a delta P, that's a change in pressure. Okay, but dP, we know that dP is equal to P2 minus P1, and that is equal to now 0.1730 into 10 power 9 Pascal. So in terms of, because the atmospheric pressure is of the range of 10 power 5 Pascal. Okay, so that means P2, the new pressure will be P1 plus this quantity. Okay, so P1 I am writing the direct value, that's 1.01 into 10 power 5 Pascal plus this value, the dP. Okay, that is equal to, now I will write it in terms in the power of 10 power 5. Okay, so that means 1730 into 10 power 5 Pascal again. Okay, so that is equal to, the new pressure will be 1731.01 into 10 power 5 Pascal. Okay, or because the answer it's asked in gigapascal, so in gigapascal it's going to be equal to 0.1731 into 10 power 9 Pascal, or that is equal to 0.1731 gigapascal. So therefore this is our answer. So let's continue with the next problem. So we are given a system of n non-interacting and distinguishable particle in a two-level system at temperature T. Okay, so let's draw the energy level diagram. It's a two-level system containing n non-interacting particles. Okay, now the energy level of 0, E is greater than 0, it's given to us, E it's greater than 0 in the high temperature limit. So this is approximation that we have to apply at the end of the result that we will obtain. What is the population of the particle in the level with energy E? So at a certain high temperature we have to obtain the population in the higher energy level. Okay, so first of all, what we are going to do is we are going to determine the probability that this energy state is occupied by the certain particle. Okay, so we require the partition function for this purpose, Z, that is equal to sum over states G exponential minus beta EI. Since no information is given about the degeneracy, so that means we can take it equal to unity, and so this is equal to exponential minus beta multiplied by 0, so that will be e power 0, so that will give us 1 plus exponential minus beta E. So okay, so that's the partition function. Now the probability that energy state E is occupied with a particle so that is given by P of E, that is equal to exponential minus beta times the required energy divided by the partition function. Okay, and that is equal to exponential minus beta E upon 1 plus exponential minus beta E. Okay, now the average number of particle in state E. So okay, so the average number of particle, so this is merely the probability. Okay, so let me call this equation 1 and this as equation 2. This equation 2 simply represents the probability that this energy state will be occupied. But when we have to determine the average number of particle in that energy state, so that's given by this expression, the average number of particles in state with energy E is given by that is equal to the n multiplied by the corresponding probability. Okay, so that means that is equal to n exponential minus beta E upon 1 plus exponential minus beta E. Okay, or in terms of kT, this is equal to n, or we can again see that by taking the exponential factor into a denominator. So while taking this the exponential minus beta into denominator, this expression reduces to n exponential beta E plus 1. Okay, or that is equal to n divided by exponential E upon kT plus 1. Okay, and then the average number of particles, so that is equal to n upon, because we have to apply the approximation that kBT, it is much greater than unity. Okay, so in that case E by kT, that's going to have a very small value. So that means E n upon 1 plus E upon kBT plus higher order term we are neglecting, and plus 1. So just to approximate that how many number of particles will be there in the energy state E, so we can also neglect this the factor of E by kT at high temperature. Okay, so that approximately the number of particles in the energy state E, they are equal to n by 2. Therefore A is the correct option here. So let's take a look at the next problem. So the energy density and pressure of a photon gas, they are given by the relationship. So let's first write the expression that are given to us. So we are given the energy density small u, that is equal to energy density u by v, and this is given to be equal to a t power 4. Okay, and also we are given that the pressure, that is equal to small u divided by 3, and in terms of total energy, this can be rewritten as 1 by 3 energy density. Okay, and if we substitute the value of capital U here, okay, from the above relationship, that is equal to 1 by 3 V, and capital U will be equal to A B T4. So V and V will cancel with each other, so that is equal to 1 by 3 A T4. Okay, now the entropy per unit volume is given by, so we are given an expression for the entropy per unit volume, that's alpha ATQ. So we have to find the value of alpha, that what is the alpha here. Okay, so we can handle this problem by making use of the modified equation of the first law of thermodynamics, which is in the modified form. We can write du, that is equal to TdS minus PdB, or after rearranging we obtain that TdS, that is equal to du plus PdB. Okay, and from here I can rewrite this as TdS by dB, okay, at constant temperature, that is equal to du by dV at constant temperature plus P dB by dV, so that will give us only P. Okay, so that means ds by dB, that is a change in entropy with per unit volume, ds by dV constant temperature, that is equal to 1 by T du by dV at constant temperature plus P upon T. Okay, so let's call this as equation 1, equation 2 and equation 3 here. Okay, so in equation 3 now we are going to substitute the value of du by dV with the help of equation 1. Okay, okay, so let's see what we are obtaining. So that is ds by dV at constant temperature, that is equal to 1 upon T, and then du by dV. So du by dV is how much? du by dV, that is equal to 8T4. Okay, so while taking a differential of the equation 1 with respect to B. Okay, so from here u, that is equal to V into AT4. So du by dV, that will be equal to AT4. So I'm multiplying here with AT4. Okay, that's du by dV. Okay, plus P by T plus 1 by T, and then pressure P. So P is equal to, from equation 2, 1 by 3 AT4. Okay, so this after cancellation of the sum of the terms, this is equal to AT plus 1 by 3 AT cube, that is equal to how much? That is equal to 4 by 3 AT cube, and that is nothing but 1.33 AT cube. Okay, so that means alpha here, it's nothing but it is 1.33. so that is our final answer. Okay, so alpha value is 1.33. Now let's take a look at the final problem. Consider two particles and two non-degenerate quantum level 1 and 2. Okay, so we are given a situation where we are having two particles, so number of particles, that is equal to 2, and we are having non-degenerate quantum levels 1 and 2. So we are having two non-degenerate quantum level 1 and 2. Okay, level 1 always contains a particle, so it's given that level 1 will always have at least one particle. It could have two also. Okay, hence what is the probability that level 2 also contains a particle? What is the probability that level 2 also contains a particle for each of the two cases? Okay, so let's see what are the options that are available with us. So in the first case, let's say when we treat the particles as distinguishable. So that's the first case, when particles are distinguishable. Okay, when we treat the particles as distinguishable, so the way we can arrange them, that's A, B, B, A. Okay, and then either we can put the both of particle here, or we can put the both of the particle here. But now listen, the condition is that level 1 always contain a particle, so that one, this is not allowed here, not allowed. Okay, because of the given condition. Okay, we have to obey the condition also. Okay, now we have to find the probability that level 2 also contains a particle for each of the two cases. Okay, so now we are having only three arrangements. Okay, where we are satisfying the condition that level 1 is always having a particle. Here we are having particle A, particle B, and here we are having two particles. So at least there is one particle in energy level 1. Okay, now the probability for the first case, when particles are distinguishable. So in this case, the required probability is, I will call this as probability 1. The probability is that two options, they are favorable. These are the two options, and there are total three options. So the required probability is 2 by 3. Now in the second case, when we treat the particles as boson. Okay, so when boson means we are having identical particle. Okay, so in that case, I can label them as A and A because they are identical. So then we will not have another option where we can write A and A. So the second option could be AA, both the particle here, and the another option is AA. Okay, now here if we just take a look at it, so this option, it's not allowed again because of the condition that's given to us. It's not allowed. Okay, because there is no particle here in the energy state 1. We are having both particle in the energy state 2, but the condition 1 is satisfied, which is that what is the initial the first condition, that level 1 will always contain a particle. So here in these two cases, we are having at least one particle in both of these two in this level 1. Okay, now the probability that level 2 also contains a particle. So there is only one option where we are having a particle in level 2. Okay, so the required probability will be, it's one favorable option, and we are having in total two options. Okay, so therefore the required answer is 2 by 3 and 1 by 2. So therefore option C is the correct one here. So this completes the discussion on the question which appeared in GATE 2017 examination.